Hello and welcome. This is Electricity and Magnetism video series part 10. Starting from today, I'm going to be talking about magnetism, which is the other half of electromagnetic theory. So far, we've seen electric fields, electric charges, forces, capacitors, and circuits. The other half is about magnets or magnetism. So the electromagnetic field is the fundamental interaction, one of the fundamental forces in nature. Remember, there are four of these: the strong nuclear force, weak nuclear force, gravity, and electromagnetism. Two of these are long-range forces or interactions, which is gravity and electromagnetism, and the other two are only for atoms and nucleus and protons and neutrons. So those are the weak and strong nuclear forces. So electricity and magnetism are linked together. And there's a very well-established theory, which was already done in the late 19th century by James Clerk Maxwell, called electromagnetic theory. And by the time we finish this class, you're going to learn these basic equations. There are four of them, okay? Maxwell's equations that describe electromagnetism. So again, the first half has to do with electric fields. You know this already. Now, what is this magnetism and how is it related to electricity and all? That's what we're going to discuss and try to find out, okay? So let's start with what we know about electricity or electric fields and see if that will help us understand what magnetism is. After all, you're all familiar with magnets, okay? You put the magnet on your fridge. You can find magnets in Earth. So we have natural magnets, or natural magnets found in Earth, or you can make magnets, okay, industrial magnets. Okay, what do magnets do? They attract magnetic material like iron. And if you put a magnet near iron, okay, if you rub them a little bit, suddenly that iron piece becomes magnetic itself, or it becomes a magnet itself. So you can make magnets, or you can use electricity. We're going to see how to make magnets. Earth itself is a magnet. The Earth itself is a giant magnet. That's how our compasses work. So compasses are magnets as well. Compass. And you can find magnets in electric motors. Electric motors. All right, so your computer's hard disk has an electric motor inside, and that works with a magnet. If a magnet is one of these are called permanent magnets. Permanent magnets. And sometimes you will have magnetism only due to currents, which you can turn on and off. And these are not permanent magnets, okay? So that would be like a wire in a coil shape or something. We're going to go into those, but let's start with really basic stuff. So what we know is a magnet, like the one you can put on your fridge, is your magnet, is attracted to the metal here. Okay, so everybody has experimented with these since the time they were kids, maybe played with two magnets. Suppose you have two objects and they magically attract each other, right? This is what you observed when you were a kid and you were surprised. How can this happen? They're not touching each other, but they're attracting each other. Okay, so possibilities are, one of them is a magnet. Let's call this A and B. A is a magnet. B is maybe just some iron, some magnetic material, a piece of iron. Then you would indeed have this force between the two. They would attract each other. Or vice versa. How about A is the magnetic material, iron. B is the actual magnet. Okay, you wouldn't be able to tell actually. That's one possibility. Possibility number two, they're both magnets. Both A and B are magnets. But that's easy to find out, okay? So if both are magnets and they're attracting each other, try flipping one of them. Let's call these sides 1, 2, 3, and 4. So keep the one on the left the same way. That is A, right? But rotate the second one 180 degrees. So 4 is on this side and 3 is to the right. Now, if they still attract each other, if attract, then only one of them is a magnet, okay? But if they repel each other, this means the forces are pointing in this direction, then this tells us that both are magnets. Why? How does this happen? Okay, I mean, why did rotating one of them change the direction of the force? This is now trying to look similar to what we know about electric charges. We have this polarity between like and opposite charges, like two positive charges would repel each other. These could be two positive or two negative charges, doesn't matter. But whenever you use the alternating charges, they would attract. So opposite charges attract and like charges repel. So when we work with magnets, especially two magnets, it all takes one to be rotated 180 degrees, and now we have a repulsion instead of attraction. So this suggests that there's a polarity issue here. Suggests polarity. In this case, we don't call it positive or negative. We call it south and north for historical reasons. So in the case of a magnet, we're going to take this and divide it into two and call one end north and the other one south. So if they're attracting each other, that's because the one facing 2, so in side 3 here, should be north. And the other one is called south. And when they repel, it's because we rotated the other one 180 degrees. So the south is now this way and north is that way. And two south poles, we call them poles now. Poles. Same poles are facing each other, therefore they repel each other. And opposite poles will attract. So that's just an experimental observation, no fact, right? Because of this change in the orientation, we have a change in the direction of the force. And why do we call them north and south? That's historical because in navigating the Earth, we use compasses. And compasses are actually magnets, made of magnets. You take a magnet and then you place it, you suspend it in air, or you place it on water, or maybe put a needle under it. And if it's free to rotate, it will align itself in the south-north direction, okay? We're talking about a geographical north-south here. So here's the Earth, a globe, right? And there's the equatorial line. Let's say you are in Houston, which is somewhere, a dot here, okay? And you have one of these magnets. And if it's free to rotate, so you make a compass out of a magnet. These are usually shaped like a diamond, like this. Okay. And maybe this one is colored. And it's suspended over a needle and then sits on a flat base. So it's free to rotate right and left. If you take that compass and hold it parallel to the ground, you will see that it's going to align itself in the geographical north-south direction like this. So this is what we call the north, geographical north. And this is the South Pole, hence the word pole, right? So this side of the magnet, which you labeled or painted, will point in the direction of the geographical north pole. And the other one will be, of course, in the direction of south. So it's wherever you are on Earth, that needle will show north. That's why we call these north and south. So why does that happen? I mean, Earth, is it a magnet? Yes, it acts like a magnet, actually, a giant magnet. So think of like a bar-shaped magnet here. Now, of course, we don't have this inside Earth. Earth's magnetism is a complex topic. It has to do with what's inside Earth. You know, there's an iron core, and then there's magma and rotation and all that. So rotation is basically why we have magnetic field. It's a complex mechanism, but don't worry about it. It's our model, okay? In our model, imagine it's a giant magnet in the shape of a bar. So this magnet, when it lines itself in this particular direction, that's because this side is attracted to that pole, okay? So suppose this was the side which you shaded was the north side. This is the other one which you call south, because that points in that direction. That's why you call it north, right? So this is north, and it's the south pole of the magnet. So if the north pole of the magnet points in the direction, the northern direction, then we deduce that using this argument. This is actually the south pole of the giant magnet that is Earth, which makes the other one the north pole of that magnet. Okay, so the south pole of the magnet is actually geographical, or geomagnetic, they call it, geographical north. Okay, so that's one similarity. We have polarity in electric fields, positive and negative, and we have polarity in magnetic fields. It's going to turn out to be a field as well, but we're just looking at the magnets right now. So the magnet will have this polarity, which we call the now north and south. Now there's one basic difference though, and we're going to understand it when we draw the electric fields and magnetic fields. So let's remember how the electric field worked. A positive charge would generate a field around it. which would radially go outward like this. And similarly, a negative charge would generate electric field which points in, radially inward. So positive out, negative in. This means in between the two charges, we would have an electric field from the positive to the negative. That's the direction of the electric field. Now note how these electric fields are starting from one point and end up at another point, okay? Now in the case of a magnetic field lines that are generated by magnets, that's the idea, right? If electric fields are generated by electric charges, maybe these poles or magnetic poles or magnets are generating magnetic fields. And when you have two magnets which are interacting, it's maybe because one of them is creating a magnetic field and the other magnet, by being inside that magnetic field, feels a force on it. Okay, that's the logic. So maybe Earth is creating a magnetic field around it because of that giant magnet, which is Earth. And the compass, the little magnet, being present in that field, is lining itself in the direction of the magnetic field. Now, if you remember dipoles, a dipole is when you fix the distance between a negative and a positive charge. Let's say you put a stick. These are two charges, and then you have a non-conducting material in between. And like this pen here, you have two charge, and it's free to rotate in any direction. But then you apply an electric field, this will rotate itself. There will be a torque on the dipole. Dipole, if you remember this from the very first electric field chapter. Just like that dipole aligns itself with an external electric field, maybe our compass is aligning itself inside a magnetic field. So that's the reasoning there. So how are we going to draw this magnetic field? Now that's the question. So I can say that safely, I guess, that where the compass is, the magnetic field should be along that direction. Otherwise, it wouldn't point that way, okay? So if you take that compass and move it on the globe, and you would mark all these directions with an arrow, and you connect those arrows, so you would end up with something like this. This can be experimentally proven, okay? Of course, try to think in 3D, okay? And you're not only doing on the surface of the Earth, but maybe in a plane, or you climb a mountain and then you observe this. So you may observe maybe at a higher altitude, a similar direction. So where the compass is, the field as a vector will be parallel to that compass. And when you're on the other side of the Earth, you observe similar things. All right. That's fine, you say, okay, but there's a problem here. In my electric field, electric charges, I knew that the field lines originated from the positive and they ended up negative. And I have this magnet here, and I may have a small magnet this size, a compass, or a huge compass or a huge magnet, which is Earth from South North Pole. And I really want to know what's happening between these poles, meaning from the south to north, okay? And how can I have giant magnets like this? I have a small magnet and giant magnet. Can I break the giant magnet into pieces and obtain charges, magnetic charges, or magnetic poles, single poles? Well, that turns out it's impossible. It's impossible if you take a magnet with south and north poles, and you break it into two pieces, and you will observe quickly that each little magnet will have its own south and north poles. And you can keep this process, you can keep doing it, try to break it into smaller and smaller parts. You will never be able to obtain a single charge by itself. Let's say you can never take this north pole apart from the south, as you would be able to do in the case of electric fields and electric charges. You can never do that. You will always get smaller and smaller magnets. For that reason, the magnetic field lines will never be from one point to another. Instead, they will be loops. So inside the magnet, we take this magnetic field line and connect it to the line at the other pole. So inside the magnet, it's going to go from south to north. Once you're outside the magnet, it's going to go from north to south. By go, I mean the direction of electric field, magnetic field, sorry. Okay, so inside the magnet, south to north, outside of the magnet, north to south. So magnetic fields are loops. Field lines are closed. They're loops. Always. Okay. Magnetic field lines are always loops. But there are similarities. For instance, in the case of electric field, we know that in a given region of space, if you have more lines, electric field strength is more there, right? E gets bigger. Like as you move close to a charge, so these are the field lines, whether inward or outward, doesn't matter. So you take an area here. There are a couple of lines. If you take this area and bring it here, there are more lines in it. So electric field goes up. Same thing happens with a magnet. When you're close to the pole, the magnetic field strength is bigger. Now, this is what you would call a monopole if you were able to observe it. But so far, nobody has seen a monopole in nature. So they don't exist. As far as we know, they do not exist in nature. Therefore, magnetic field lines have to be loops. Okay, so as you see, there are similarities and there are also differences between electric and magnetic fields. By the way, the letter we're going to use for magnetic field is B. Electric field was E. Magnetic field, we're going to call, or we're going to use the letter B for magnetic field. So when you have a magnetic field present, this could be Earth's magnetic field or any other external field, and then you take a piece of magnet and place it in this region where you have the magnetic field. It'll align itself. There will be a torque on the magnet, and you're going to end up with a magnet which is parallel to the magnetic field. All right, good. So that actually stands for the force. Remember, for the electric field, we had this force, which was given by Q times E. Did I write the formula here? No, the electric force is Q times E. If charge is positive, the force is in the same direction as the electric field. If the charge is negative, it will be the opposite direction. So we have a similar force on magnets when they're placed in magnetic fields. Now, this doesn't really answer the question why we have magnetic fields in the first place. Yet, this is actually well understood. I mean, Maxwell's theory and the experiments by Oersted and Ampere tell us where and how the magnetic fields are generated. It's really interesting because it goes back to the idea of charges. A charge creates electric field. When you start moving it, it creates a magnetic field. Moving charges create magnetic field. And it's not only the magnets which are affected by magnetic fields, charges are also affected by magnetic fields. The rule is, though, they have to move. Also, moving charges experience force in magnetic fields. But they have to move, okay? These have to be moving in order to experience this force. For electric field, we didn't have that condition. A stationary electric field and stationary charge would interact. If you want to have a force on a charge in a magnetic field, the charge has to move. And that's also an experimental fact. So let's talk about those experiments. It was first Oersted, who observed a compass needle moving when you turn on an electric current. So let's come up with a setup like this. Let's say we have the table top here, and then make a hole here in the tabletop, and then let a wire pass through it like this, and connect this to a switch, and then maybe a battery here. So that when you turn on the switch, there will be a current in the wire because you have a complete, okay, if you want, and the resistor somewhere if you don't want to short your battery, okay. This is very similar to what Oersted did, but he had a compass with him. They say it was an accident in the beginning. For our case here, let's place this compass right here. Let's say this is the north direction, okay? And this is your lab room, this is the north, and this is south. And this would be west and east. So what do you expect? The compass would line itself in the north-south direction, right? This is your compass. It doesn't matter where you put your compass. The switch is not on yet, so it'll always align itself with the geographical north, whether you're here, there, or there. So this is a slightly different version of Oersted's experiment. But you have these compasses laid out on the table. They always point in the north. But once you turn on the switch, close the switch, now we have a current. Suppose this was the positive side, and this is the negative side. So there will be a current up this way. That's your current. What Oersted observed was this compass did not change its position. And this one suddenly flipped 180 degrees, as if south and north were swapped all of a sudden. But he didn't observe it on this one. And this compass here rotated 90 degrees. came like this. And this one over here also rotated 90 degrees with the compass at 90 degrees right there. And when he opened the circuit, opened the switch, and the current is gone, the compasses went back to normal, pointing in the geographical north. And that was surprising. So he probably took his compass and moved around the wire on the table to see what direction. I mean, it's obviously affected by the current, right? And we know that in order for a compass to move, there has to be a magnetic field. So he realizes quickly that electric charges moving, which is nothing but the currents create magnetic fields. And if you do this experiment at various points, you can easily find out that the loop in this case will be simply a circle of a fixed radius. Along that circle, you will have a magnetic field. All right. Now, if the current is upward, you would have the magnetic field in a certain direction. And if you switch the polarity of the battery, suddenly the current now is downward, and the magnetic field also changes direction. You observed. Okay, that's Oersted's experiment. And the direction is not arbitrary. The direction depends on which direction the current is. The direction of the magnetic field depends on the direction of the current. And there's a rule to find that direction, which I'm going to talk about later. It's called the right-hand rule. And the other experiment was done by Ampere. When he found out about Oersted's experiment, he said, okay, electric currents generate magnetic fields. And the reason why a magnet, a compass, experiences a torque when placed in a magnetic field is because that magnet also has a magnetic field. So we're talking about two magnetic fields interacting, he thought. So what if he says, instead of using a compass, what if I use another wire? So I take that current carrying wire and lay it on the table like this. Okay, here's my battery, the switch. So here's the current. So what I do is I take another wire and lay it parallel, let's say, to the first one, the battery and the switch and all that. And if I turn on both switches, so now I have current on both wires, I suddenly see that these wires are attracted towards each other. So two current carrying wires interact without touching each other. And that's because one of them creates a magnetic field and the current is affected by that magnetic field, or vice versa. You can think about the other way. You know, this is current 1 here on the right and current 2. So current 2 is interacting with the magnetic field current 1 generates. That's one point of view. Or current 1 is interacting with the magnetic field current 2 generates. You can look at it both ways, and which will be, both of them will be correct. And he also observed that if you change the direction of the current, instead of having two parallel currents, if you have opposite directions, now they would repel each other. So those are the famous two experiments. Let me pause for a second. Okay, so that's Ampere's experiment, which shows that two current carrying wires will exert forces on each other. by the way, these forces have to obey Newton's third law, the action-reaction principle, right? The force on wire or current 1 due to the second current has to be equal to the other one in magnitude, but opposite in direction. You can write it mathematically like this with a negative sign, equal but opposite. So if you have two currents moving in opposite directions, this force would be a repulsive force. So what does it suggest, though? I mean, what is current? Current is charges in motion. So what we really have is actually a force on moving charges, which is the point that I was making here. Moving charges experience a force given an external magnetic field. So we have a charge, Q. That charge has to move. So we have a velocity vector associated with it. And we have an external magnetic field. Therefore, there will be a force. Now, we already know the direction of the force, because by definition, the current is the direction of the motion of positive charges. So, if you go back to the example of, or experiment of Ampere, the positive charges are moving, for instance, in this direction. In reality, it's the electrons moving in the opposite direction, but don't worry about it. You know, that's the direction of the positive charge. So we're gonna generalize this, okay? We're gonna say, if there is a single positive charge moving in a magnetic field, there will be a force on it. Now, if this force is in this direction towards the other wire, so we have this V pointing this way, and the force happens to be in a direction perpendicular to that velocity vector. So we have the Q, positive charge, we have the force, and we have the velocity. Where is B? Now the convention that we found, or the direction we found using Oersted experiment. Remember I mentioned the method of finding it called the right-hand rule. Now I can talk about it again. So put your thumb in the direction of the current. And these fingers, when you curl them like that, that's going to give you the direction of the magnetic field. So if the current is upward for the Oersted experiment, you end up with a circular loop. That will be the direction of the magnetic field. So in Ampere's experiment, wire number 1 or current number 1, put your thumb in the direction of that current, and these fingers, when they curl or wrap around that wire, like this. Okay, let's use red. Like that. This will be the magnetic field. Okay? Concentric circles around that wire is the magnetic field. So where the second wire is, magnetic field should be upward if you follow that circular loop. Where you have the second wire, magnetic field should be pointing up, because that has to be a part of a circle around current carrying wire number 1. Therefore, it has to be up. So where Q is, the magnetic field is actually up. Up means it is also perpendicular to F. All right? That's a very important result. This force will be perpendicular to both velocity and the magnetic field. What about the angle between the magnetic field and the velocity? In this particular example, it is also 90 degrees, but it doesn't have to be. In general, it could be actually any angle except 0. If B and V are parallel, there won't be any force on the charge, or anti-parallel. So 0 and 180 are exceptions, but in general, the angle between B and V can be anything. That would not change the result. That is, force would still be perpendicular to both B and V. So think about the plane that vectors B and V form, right? Two vectors, no matter what the angle between them, will always define a plane. This force will be perpendicular to that plane. Okay? And actually, there's a second version of the right-hand rule, which will give us what the force, which will give us what direction the force will be. Remember, the first one was you put your thumb in the direction of a current and curl your fingers, wrap your fingers around the thumb like this. That will be the direction of the magnetic field loop. That's rule number 1, or version 1. Version number 2, use these 3 fingers, a thumb, index finger, and the middle finger. Put your thumb in the direction of velocity, thumb velocity. Index finger, magnetic field. Okay, any angle between them is okay, except for 0 on 180. V, B, then the middle finger, which is perpendicular to both index and the thumb, is the force. All right? So when you're watching this video, try to do it using your right hand, not the left hand, the right hand, okay? The thumb in the direction of velocity. Magnetic field, index finger, and the middle finger will show you which direction the force is. So that's what we call a cross product in mathematics. A cross product of the vectors V and B. So experiments show that the force is linear with both V and B. If you double the velocity, you double the force, etc. And Q is also is linear. F is linear in Q. So F will be equal to Q times V cross B, right? This gives the force on a moving charge in the presence of a magnetic field with velocity V. Okay? Now, if the charge is positive, the direction of the cross product is the direction of the force. But if the charge is negative, once you determine the direction of the cross product, meaning V cross B, this is V cross B, V thumb, index B, so this is V cross B. If Q is negative, F will be in the other direction. Okay, that's how you think about it. You first determine the direction of the cross product V cross B. If the charge is positive, that is the direction of the force. If the charge is negative, just flip it 180 degrees. That's how you find the direction of the force, magnetic force, okay? FB, if you will. What if there is an electric field also present? Yeah, I mean, it can happen, right? What if there is also an electric field in that region? There's a force on it given by this formula, Q times E. So I combine the two. I combine the two and call this the Lorentz force. It even has a name. Lorentz. I'm not sure if there's a T there. Lorentz force. All right. That's another example where electricity and magnetism are put together. They're related. Okay. If you want to learn advanced physics, when you read about Albert Einstein and his theory of relativity, special relativity, you'll see how he understood electromagnetism with from a different perspective and using mechanics, Newtonian mechanics. He achieved a better understanding of what's going on. So at any given time, you have both electric and magnetic fields are present, but how much do you have? How much electric field? How much magnetic field? Okay, that depends on how fast you're moving. All right. So these are called transformations. So you can transform some of the electric field to magnetic field, for instance. It's like two sides of a coin kind of deal. All right, but that's for advanced. But still, we can observe the relationship between electric and magnetic fields in many places, even without doing advanced stuff like Albert Einstein's theory of relativity. Okay, so again, how do we know about this relationship? By experiment. Because we observe that when you place a current carrying wire in a magnetic field, there will be a force on it. And then we think backwards. What is a charge? What is current? Current is charges moving. So it must be actually the charges that move that will experience this force. Okay, of course, if you think deep enough, these are really simplistic explanations. Within a conductor, if the charges are experiencing a force, shouldn't they be moving to one side of the conductor and leaving the other side the opposite charge? No, those are legitimate questions, which you may find the answers if you study more. But for now, I think this is enough. This is why we have a force on a moving charge from the basic experiments of Ampere. We can deduce, or we can find out this relationship. Now, if this tells us more, let's check the magnitude of the force real quick. So it's a cross product, right? I'm assuming that you guys all know what a cross product is. All right, that's not just for electricity and magnetism. The cross product happens everywhere. And from mechanics, torque, for instance, or angular momentum, right? These are the places where you've seen cross products before. So if you want to write the magnitude of this force, there is, of course, Q. I'm going to show the magnitude by these bars here, right? There's Q, and a magnitude is always a positive number. So if it is a negative charge, make it positive, right? So the absolute value of Q, the magnitude of V times magnitude of B times the sine of the angle between the vectors V and B. In particular, if theta is 90 degrees, sine 90 is 1. But this is what I want you guys to think about now. Don't worry about the sign. It's a dimensionless number anyways. Check the units here. So F is in newtons. Charge is in coulombs. Velocity is in meters per seconds. So what is the unit of the magnetic field then? Now, in order to have newtons on the left-hand side of the equation, this must be equal to newtons times seconds divided by coulombs, right? And divided by meters. Because if you multiply it by coulombs, meters per second, you get rid of those and you're left with newtons. But we already know that current is charge over time. So it is coulombs per second. So 1 amp is 1 coulomb per second. I have seconds over coulomb here. So that would be equal to 1 over amps, right? So the unit I have here is newtons per amp meters, or we're going to call it Tesla. So 1 Newton per amp meter is what we're going to call from now on 1 Tesla. Okay, the unit for magnetic field in standard units where we have meters, kilograms, seconds, and amps. 1 Tesla is equal to 1 Newton per amp per meter. Now, Tesla is a big number, okay? A magnetic field of 1 Tesla is a lot. Now, compared to Earth's magnetic field. Earth's magnetic field is in the order of magnitude of 10 to the negative 4 Tesla. That's why sometimes we're going to use another unit, which is called a Gauss, okay? A Gauss. So 1 Tesla would be equal to 10 to the power 4 Gauss. All right, so this is Earth's field. Earth's magnetic field. Whether it's Tesla or Gauss. That's the magnetic field. But if you want to use newtons, amps, and meters, of course, it has to be in Tesla. And this gives us the electric field, force on a moving charge in the presence of a magnetic field. If there's electric field, you have to include it. That's what the Lorentz formula is for. So let's try to think of an example where we could have both, right? So what if we have this capacitor or parallel plates. So let's say this is positively charged on the top and negatively charged on the bottom. Therefore, we have an electric field which is pointing downward. So a positive charge, positive Q, would experience a force in the same direction as the electric field. So this part here, Q times E, I'm talking about, FE, if you will. Now, if the charge is not moving yet, that is the only force you have. The only force you have is due to the electric field here. But what if the charge starts moving? Let's say it's moving to the right. Now, this electric force would still be there, whether it's moving or not. But if it is moving, then we have to consider magnetic fields. Do we have a magnetic field? If there is one, there will be a force on it. Okay, the only case where you would not have a magnetic force, which is the second term in the Lorentz force, is when the magnetic field is parallel to V or anti-parallel. But except for those two, you would indeed have a magnetic component of this force as well. So let's come up with a direction for magnetic field. How about a magnetic field which is going into the page? Okay. Now I'm going to use a symbol here, which is going to be a cross in a circle, and that will be the direction of the magnetic field. So here's the convention. If I use a cross in a circle, this means into the page, or monitor if you're watching this video, into the plane, into the page, let's call it. And if it's coming out of the page towards you, if that's the direction of the magnetic field, just put a dot inside a circle. a dot inside the circle. That's out of the page. Okay, in our case, into the page. So there will be a force on the moving charge because the angle between V and B is not 0 or 180. How do we find it? Again, the right-hand rule. With your 3 fingers, it's a positive charge, put your thumb in the direction of the velocity and index finger in the direction of the magnetic field. Okay, you guys do it when you're watching this video. Take your right hand, not the left hand, right hand, thumb in the direction of V, index finger in the direction of magnetic field, and then you would have a force which will be pointed by your middle finger. So in that case, it will be upward. This way. This will be the magnetic component of the Lorentz force. All right. If it so happens that this motion is along a horizontal line, this can only mean that these 2 forces are equal in magnitude. So if Fe is equal to Fb, this means that Q times electric field is equal to Q times V times B, right? Special case. If you change the charge on the capacitors, that would change the electric field, and then you would have now the force is not equal to them each other anymore. So you would have some acceleration because the charge will move under the influence of a net force. What if you turn off the electric field? Okay, so let's take a look at another example where you don't have electric field, only magnetic field. So let's say here we have the charge, the positive charge, and moving to the right. And it's going to enter a region where we have magnetic fields. So magnetic field is, let's say, into the page like this. These crosses or cross in a circle means magnetic field is pointing into the page. This is B. So according to right-hand rule again, V cross B is up. At that instant, it will experience a force this way. Does it mean it's gonna go up? No, it already had a velocity, remember, to the right. Think of projectile motion, okay? You give it the horizontal velocity, but Earth pulls it downward, so it starts to change its direction. So what you expect here, in a fraction of a second, this particle will not move to the right, not to the left, but somewhere in between. So it's going to end up here. Okay, I'm exaggerating right now, but if it's moving from this point to that point, this means the velocity vector changes direction. That's what happens when there's a force, right? So now the velocity vector points this way, but it's still inside the magnetic field. And remember, force has to be always perpendicular to both magnetic field vector and the velocity vector. So when the particle moves from this point to that point, now the force is this way. So it has to be perpendicular. The force changes direction. Apply this logic again. You know, a tiny fraction of a second later, now because of this new direction for the force, the object will end up here with the velocity vector pointing even this way. But it's going to end up with a force vector still perpendicular. So if you keep adding those points, you will end up with a path like this. And if you carefully draw this, it's going to become a circle. Now imagine you had the magnetic field on this side as well. So you can complete the circle this way. It's going to come back to the same point. Okay, it's going to go in circles. If you keep the magnetic field strength the same, there is no reason why the charge should end up at a different point. It's going to just complete the circle with a radius r. Now, if you know the mass along with the charge, you can even write down an equation, because we know how circular motion dynamics work, right? If you apply Newton's second law, now the net force is nothing but this QVB, right? Now the angle between V and B is already 9 degrees, because any vector on this plane will be perpendicular to the magnetic field, which is into the page. So sine 90 is 1. So the force is simply QVB. That's the left-hand side, the only force acting on the object. That is a centripetal force pointing to the center, which is now equal to the mass of the particle times its acceleration. So in a circular motion, the acceleration is centripetal acceleration, which is given by v squared divided by r, the radius. Okay, so now you have a relationship between these variables. You can get rid of one of the v's. All right, so if you write b as a function of everything else, now it's equal to mv over qr. So if magnetic field is a constant, v and r, if you change them at the same time, you can keep v a constant. So all right, that's the relationship between the two there. Greater the velocity, greater the radius of that circle. All right, so that was another example of an application of this Lorentz force without electric field, just the magnetic field. Now, what if there is an angle between, an angle meaning not 90 degrees, between V and B? What if the particle enters the field with an angle? Now, the velocity vector will have two components. Number one will be perpendicular to B, and the other one in a particular direction, which is along B, I guess. So along the magnetic field, there won't be any force. The force is perpendicular to the field, but it already has a velocity in that direction. So what you will end up with in that case is not a circle, but a helix. Okay, so try to draw this on your own. Try to find out the direction of the force and the velocity direction, the magnetic field, and see how right-hand rule applies. Okay, that's a homework for you. Try to find out how you get this helix. So the velocity will have components. Obviously, you have a component in the direction of motion. And then you have this circular part as well. Okay. This force, in the case of the circular motion, doesn't do any work. Okay. In order to have work, you would take the dot product of the force by the displacement vector. So work would involve the dot product of some displacement. You can write as an integral if you like. So f dot dl from any point to another point. But since force is perpendicular to that dl vector, as in the case of a circular motion, you will get 0, right? Cosine 90 is 0. So this will be 0 in this case. The magnetic field would not do any work. Electric fields, on the other hand, let me say the forces due to electric fields, they would do work. But the forces due to magnetic fields wouldn't do any work. Okay, so that is the Lorentz force. Now we'll have a similar formula for the forces on current-carrying wires in the presence of external fields, which is going to look similar, but I'll leave that for the next video. And let me stop here. And in the second video, I'm going to talk about the force between two currents, and then solve more examples. And probably in the video after that, I'm going to move on to sources of magnetic fields. So we know how wires, current-carrying wires, are influenced by magnetic fields. What about magnetic fields generated by moving charges or currents? It works both ways. So there's a lot to investigate, okay? So let's say current will generate magnetic field, but a current inside a magnetic field will experience a force as well. Okay, so it works both ways. And this means moving charges create magnetic fields, and moving charges will also experience a force when they're placed inside a magnetic field. Okay, so if the Earth is generating a magnetic field on its own, that's because there's a charge flow inside the Earth that is creating this magnetic field. All right, so I'm going to stop this video right here. And the next video, I'm going to talk about forces and currents.